All right, so we're going to continue where we left off. We're going to take our grammar type here and we're going to do some calculations with it, which are going to be important for actually building a proper parser. So how do we want to go about doing this? Let's go ahead and just organize things a little bit. Let's create a file called grammar rs and actually move all of the code that we've written so far into grammar rs. And then we'll go over here and we'll do mod grammar and pub use grammar star. And then we're also going to do test.rs. And then in here we're going to say cfg test mod tests. Did I call it test or tests? Call it tests. Then we're going to go over into grammar.rs and we're going to grab this one test that isn't really a test because it has no assertions, and we're going to say test grammar. And like any good test, we're going to start off by making it fail and we're going to run it. I'm missing something. What am I missing? What am I missing? And we need to use superstar. There we go. So our test is failing. So what we are going to start off with is grammar.symbols. And we're going to into iter.map symbol.name collect. That's going to become a vector of strings. And so the symbols that we have here should be the same as A, B, A, B. And then we're going to do into iter.map ss.toString.collect. And if that doesn't give me any, oh, so did we not write this useful little function here? We wrote rules, but we did not actually write symbols. Let's go ahead and do that. Symbols. And again, this symbol actually has a parameter, a lifetime parameter g, but that gets picked up by the self parameter here. So what we're going to do is basically it looks like this, where for every symbol we're going to do symbol with grammar and the symbol idx there, symbols.len. There we go. And then this should be okay, except for the fact that let symbols expected actual. And then the natural order for those things is actually going to be that. There we go. Cargo test. We'll see. One passes. We have that. Just for the sake of making this as a general convention, we're going to put the, I don't want to have to say capital A versus lowercase a, so we're just going to rename these to X and Y, and then over here, similarly, we'll make sure that that doesn't break the test. Excellent. So, we want to do, let's open up another file. And then here, I'm just going to go ahead and use superstar again, because that'll just make it easier. We'll do struct analysis. Let's make this pub crate struct analysis so that I can use it from the other parts of the code, but at the end of the day, do I really want to expose this for people to look at? Yeah, I guess I do. Let's make that pub. So what is the analysis that we're trying to build here is there's two analyses that are going to be useful, and that's going to be a list of nullable objects. Well, it's going to have a grammar in it. So we're going to have a lifetime parameter g, a reference to a grammar. We're going to have a bunch of symbols belonging to that grammar. Hash set, we're going to import that from collections. And then the last thing that we're going to have is the, I call this first follows. And we'll define that in a second. Let's ignore that for now. Let's start with the nullables. So we're going to do impl analysis pubfun build, and we're going to take a reference to a grammar. We're going to need that tick-g in scope. So tick-g our grammar, and then that's going to give us an analysis tick-g. So it's going to need the grammar itself. You're going to have to name that parameter. Undeclared use of tick-g lifetime, okay. And then for nullables, we're going to just set that as hash set new for the time being. Get that to all compile associated. What does this say? That's just a warning because I have some unused stuff that we will flush out. So the first thing we want to do is, we'll just call that nullables. Do you even need the grammar in here? Maybe you don't need the grammar. The grammar would be useful if it wasn't that every, oh, well, we'll keep the grammar. We'll keep the grammar. So for the nullables, I'm just gonna make this so it takes that grammar as an argument, and it's going to give us the hash set of symbol G that we're looking for. And this is actually just going to be self nullables grammar over here. And to do that, so to calculate the nullables is going to be the general strategy that we have is going to work like this. So the easy part is to look for any rules that have the form alpha to epsilon. So if I have alpha to epsilon, A to epsilon, B to epsilon, obviously A and B are both nullable. If I have A goes to X, the presence of this rule has no effect on A being nullable. If I have a C here that generates Y, C does not get added, but if I have D that goes to Y, and then I also have D that goes to B, well, here is an interesting case because D will go to B and B goes to epsilon, and so this will actually add D even though D doesn't have a production of the form D to epsilon. It's kind of a derived production, if you can think of it like that. So D goes to B and B goes to epsilon. Another way you could put it is if I have another case that we have to consider is E goes to A, B. Now here, neither A being nullable and B being nullable, because they're both nullable, so must be E. So the general strategy is first we look for anything that has an empty production rule. That is, A goes to epsilon. And again, that's going to be in our code. It's going to look like a, and then the list that follows that is going to be like an empty list, kind of conceptually. We'll put that in quotes. So we're going to look for everything where the production is empty, but then we also have to play this game where once we say A is nullable or B is nullable, we have to kind of go through the rest, and anytime that we see a symbol over here, we have to kind of get rid of it, and then once one of the rules becomes empty, then that gets added to the list of things that are nullable. So it's an iterative algorithm. We're going to continuously look for anything where we have ruled out or eliminated everything on the left-hand side, or on the right-hand side. So we're going to do let nullables. This is going to be our result. So we'll do hash set new. And then we're going to make a loop, and we're going to use a loop because we don't know ahead of time how much we need to loop. We're going to loop until we hit a stable state, and a stable state would mean that we go through an iteration of the loop and nothing has changed. So what that means is we're going to set up a Boolean flag that lets us know has there been any changes on this particular iteration that variable is declared inside of the loop, because every iteration it gets reset. And then the very last thing, we're going to do a bunch of stuff, if dirty, if not dirty. So if we go through the whole iteration and there's nothing that we removed, we apparently have found everything, and any future iterations of the loop are there's no more iterations of the loop, because any further iteration would have no effect. It would just produce the same set again and again and again. So we are going to keep track of this dirty flag, and what we're going to go through is iterate through all the rules. So for rule in solve.grammar, oh, that's not solve.grammar because we're not inside of a, well, it's a method, but it's not a method on the type because it doesn't take a self parameter. There's no self here. So we're going to go through all of the rules in the grammar. And then we're going to ask, first of all, we're going to ignore the left-hand side. So if the nullables does not contain the left-hand side, so that means that I think we could leave this, condition out, but this is going to help us walk over rule, or just short-circuit rules where we've already decided to include things. This test here is actually completely optional, but we'll keep it here anyway. So we're going to skip over cases that we've already crossed out for A or whatever. We're only going to consider the rules that we haven't eliminated. If the rules right-hand side, and we're going to iterate through all the rules. And then what we want to know is, are all of the symbols contained in nullables? What am I doing here that's wrong? For rule and grammar, there we go. Nullables contains symbol. What's wrong with this? Oh, EQ is not satisfied. Let's go ahead and add some EQ on our symbols. Where should we go for that? So symbol. When we want to compare two symbols, we're going to run into some issues, because when we want to compare the grammars, the grammars are references, and you can't compare references with the EQ, with the equals operator. So what we're going to do is impl for every lifetime, we're going to do standard ops. We'll start with partial EQ for symbol tick G. do we not need to import that? Is that not where it lives? So we're going to do EQ. And so we can do stdmem, I think it's stdmem putter EQ, is it? Or is it, I guess it's self.grammar.putter equal other.grammar other.grammar, and self.index equals other.index. And I forget where putter equal lives. It was in fact in std_putter eq, and we're going to take the one grammar and the other grammar and compare them for equality. There we go. We're going to do something virtually identical for rule. When I say virtually identical, I mean literally identical. And then we're also going to do EQ for symbol, which this is an empty body because it doesn't actually define any more methods. There we go. So now we should be able to say expected. Oh, this needs to be a reference here. So to use a hash map, we need to have hashable as well. And we can go ahead and add that. Impl for G. And when we want to hash, we're just going to do self.index.hash. 0.hash. And we're going to do that for the other one. Again, these two things should mostly be equal because we're just comparing pointers on these things, hashing the pointers on these things, and all of a sudden I can use hash tables for containing these rules. So, where were we? We're going to iterate through all of the rules in the grammar. For anything that hasn't already been added, any rule whose left-hand side hasn't already been decided that it's nullable, we're going to go through the right-hand side, and if all of the right-hand side, each of the right-hand side symbols is a nullable symbol, then we're going to do nullables.insert rule.lhs. We add the left-hand side to the list of nullables, and then we set that dirty flag, and that has the effect of saying, okay, we found one that could potentially affect the, that could potentially cause a cascading effect, so we're going to iterate the next time we get through the loop, and this is our nullables. So let's go ahead and add some tests for this. Test nullables. So we're going to use the same grammar here. Actually, we're just going to copy the whole test and then modify it. So the same, well, we're not going to use the same grammar. We're going to use this example grammar that I have over here. So we're going to have all the way through E. And then for A and B, we're going to have two empty productions. We're going to have for I'm actually going to change it slightly. Have it so that, oh, no, let's not change it. A goes to X. C goes to Y. D goes to Y. E goes to AB. And then we should have the nullables, which we will figure that out. Nullables expected. We'll do let analysis equals grammar analysis. Is that what I called it? Build grammar. I just called it analysis. We're going to plug in the grammar there. And then the actual nullables are going to be analysis dot nullables. This up. We're going to change this to be not nullables, but calc nullables, I guess. Pub fun nullables self. We're just going to clone that. Why not? Again, keep calling it tick A rather than tick G for grammar. Our symbol needs to be, we need some things to be clonable here. So actually we want these not just to be clonable, but derive, clone, and also copy, because all of these are primitive types. Okay, so we have nullables, and in our tests, nullables should be public. I mean, this isn't going to work, but so what do we expect to be nullable inside of our example here was A, B, D, and E. A, B, D, and E. And then this should be a hash set on both ends. We'll add that as an import to our tests. And this should be, we need to dot map. I guess we need to do into iter symbol dot name, and then collect it. There we go. And now we can cargo test, make sure, nullables failed. A, B, D, and E. Did I not write that? A, B, D, and E. Right? A, B, D, and E. Why did E not work? Make sure that I have the order in the right place. So what we actually got, no, the actual comes first. Okay, So we did not get everything that we were expecting to have. Why is that? So A and B should be in that list. D, oh, I forgot one of the production rules is D goes to B up here. 1, 2, 3, 4, 5, 6, 7. There are 1, 2, 3, 4, 5, 6, 7 rules there. That should fix it up. Okay, so we have our nullables code. Okay, then the next part is a little bit more intense. So we do we actually ever use this? I don't know if we actually use it. We'll get rid of that. Just get rid of the complaints from our linter here. And then similarly, when we do this, we want to pub use that and pub use that. So that should get rid of some of my errors. Warn dead code. Struct is never constructed. Pub struct. Are these actual errors? Grammar analysis is never constructed. Oh, derp. I actually meant to do that in lib.rs. Here we go. And so next we want to calculate the first and follow sets. So the first and follow sets are a little bit more difficult to calculate because they tend to have this circular nature to them where let me just look for the test that I have in my other implementation. We will go through and copy some of these. And so test first. So we're going to create a new grammar. And most of these are going to be variations on this just to keep things consistent. We have X and Y, and we have just A. And the rules are X and Y and build. Let A equals, yeah, that's right. Do we want to do it like this, or do we want to continue doing it the way that we have it up here? Let's go ahead and add a little helper method here, impl grammar. We'll do symbol. We'll do option symbol in self.symbols. So we're going to go through and look for a particular symbol name. I'll just have it as a stir there. We can make this s as ref stir. If symbol.name is equal to name.asRef, and we're going to return symbol. The grammar is self, and the index is, just go ahead and rename this. And that needs to be wrapped up in a sum. And otherwise we're going to return none. Oh, that's right. Symbol idx equals symbol. And that, no, is index. There we go. So now I can do this. I can do let a equals grammar dot symbol a unwrap. And I'm going to leave these lowercase just because otherwise Rust will complain that I have violated the naming convention. But we are going to have assert EQ on here. What is this? Test first. AX, AY, grammar symbol. Okay, and then we're going to do A dot firsts, because there can be more than one first, is going to be X and Y iter dot copied dot collect. So we don't have our firsts, and so oh yeah, that was one thing that kind of ran into ran me into originally I wanted this to be such that I could call the symbol dot firsts, and at the end of the day, that was causing me to my first iteration of this was causing me to have to recalculate, recompute this analysis data structure a whole bunch. So we're going to do let grammar analysis equals grammar analysis build grammar, and we're going to build it from the grammar. I'm just going to call it analysis, and then I'm going to have analysis.firsts of A, and so we need to go to the analysis, and we're going to create a couple stubs here. Firsts, I'll call it first of self symbol, and that'll be a hash set, because I'm going with hash sets apparently, and we'll call that a to-do. And then let's call that first, why not? And then we'll call this follow. So going back here, we've got analysis.first of A, local variable with a similar name exists. There we go. So we've got test first. There was a bunch of cases that I ran into that were worth writing out. Test empty is a case where we haven't. Just so I don't go crazy, I'm going to actually reverse the, we'll keep the order here. Here we have test empty only has one symbol. We have A, B, and C. Let's get a couple of those. And then A leads to X, A also leads to empty, B leads to B leads to A, and C leads to X. So this is sort of a test of whether or not our nullables are going to, this is very similar to the first test, the test nullables. Test nullables with empty. Not the best test in the world, but whatever. And we're going to have A and B, and then what does this say down here? We need X. and the nullables here are going to be A and B. Do I need this X here? No. So test nullables with empty works. That doesn't surprise me. Test first is failing because we haven't actually implemented it yet. Let's get a test that I'm not going to bother copying all these tests here. Test follow. So for this test that we want to write, we have A and B, we don't have a C, and we have symbols X and Y. A leads to X, B leads to A followed by X, and B also can lead to A followed by Y. And we need A, X, Y, and then we're going to grab our analysis, and then we're going to do analysis.follows of A is going to be X and Y. Let's call that follow. Okay. So what does this, what do we need to make these things work? And because we want the first and the follow together, I'm actually going to reorder these tests here to put that down below. Okay, let's start off with this simple example here. So for this grammar, it's the easiest thing in the world. We have a non-terminal A, and it produces X, and we have another rule, same non-terminal A produces Y. This means that the let's actually modify this slightly. Let's do B as well, goes to Z. So this is our grammar, this is the test. And what we want to do is calculate the, what do we actually write? The first of A. And the first of A should be the set of all terminals that A can produce. It's the set of all terminals that when you expand A, eventually it has to reach one of these terminals. So in this case, it has to either expand to X or it expands to Y. So in this case, the answer should be X comma Y. And the way that we do this, the way that I ended up doing this was I had created a graph representation of things, because sometimes the first will depend on the follows and vice versa. And I don't have an example handy off the top of my head, but sometimes you'll end up, let me see if I can't think of a situation without messing this up. Let's just go ahead and copy that and start a new sketchpad over here. We're going to say this, and then we'll also say C will be A and B, and C could also be empty. So here's, maybe this is good enough to start with. So just kind of thinking intuitively, the first of A well, the first of B is really simple here. The first of B is going to have to contain y. We can see because you look at B and it produces a y. And I think in fact that's the only thing that it can that is what the full set first of B here is the set y. But then when you want to calculate the first of A, something more interesting happens because the first of A, the first symbol and the only rule for A is a non-terminal. And so the first has to be a set of terminals. What that means is that in order to calculate the first of A, you actually have to calculate the first of B. And in this case, that's the only thing that you need. And so there tends to be, and then in the case of C, it is harder. Let's just finish up the example and then we'll explain. If we're going to do the first of C, do I like this example? Do I want to do... coming up with good examples is the hardest part. The first of C is going to be the first of A. No, this isn't the example that I wanted to give. We will do one. No, we can change this around. We'll change this around just slightly, turn that into another A. So when we see that so C goes to A or B, so that means that either the thing, the first symbol that starts off with C has to be the first one of A, but it could be that the A expands to an epsilon here, that it turns into the empty string, and we actually have to get the first of B as well. This isn't the best example. Nuts. And this is not equals. This is a union here. It's a union with the first of B. And then something like this, where you have D goes to A. Here's an interesting case, is when you have a rule like this, the first of D is going to be the first of A, but it's also going to include the follow set of A. Why the follow set of A? Because if A expands empty, if it has no expansion, if it expands to an epsilon, the empty string, then D will actually be, will expand into, does that work? I don't know if that works. Well, let's look through the algorithm that I had, and then we can try working through it separately again another time. So we're going to define a data structure first follows, which is actually a graph data structure. So the point that I was trying to get to here, is that this is the general structure of how things are going to look, where some thing that we're trying to calculate is equal to a union of a bunch of other things that we could potentially have started with. So the first of A is going to contain, and I'm going to use a just an arrow to mean contain. Well, I'll use the reverse arrow here. So it's going to contain the first of B. the first of C, on the other hand, is actually going to contain the first of A and the first of B. So we're going to add that to this graph, and then anything that we find in our calculation, we're going to draw an arrow from the thing that is contained to the thing that does the containing. And then similarly, once we have first of D down here, it's going to have both a first of A inside of it, but also a follow of A inside of it. And we're gonna do that for all the different combinations. So we're gonna have follow of B, we're gonna have follow of C, and all these things. Follow of A is already there. And so however we're going to do this, we're going to stitch together a graph of all the different containments. And then in cases like first of B, where it contains a clear concrete terminal, we're going to just put that as the singleton set. So the singleton set is contained inside of first B, and that just is another way of saying that Y is an element of first of B. So we're going to define this graph data structure. First follows of G, and we're going to define it down here. It's also going to have the grammar inside of it, just in case we need it. We're going to have the edges, which is going to be a what do you call this again? The representation of a graph where you just keep a vector of all of the different outgoing edges or incoming edges or whatever it might be. So these are going to be the edges from a particular kind of node. We're just going to call this a first follows node. And then to a set of first follow nodes over here. And then we need to define what that first follow node is. And the first follow node is going to be an enumeration that just tells us what are the nodes in the graph. It's either going to be the first of a symbol, the follow of a symbol, or it's going to be a terminal, which is just going to contain the symbol itself. And again, I keep using tick A instead of tick G. And we're going to need to add the hash map to our imports list. And then we are going to do something similar to the calc nullables. We're going to calc first follows, and that's going to give us there we go. So this first follow structure is a graph, and so we're going to add a few convenience functions methods on here to make it easier to work with the graph. First one is we're going to have a new. Takes a grammar, and we're going to get a first follows G, and that's going to be for the edges, we're going to do a hash map new. The next thing we're going to add is a way to link to add an edge to the graph. So the graph starts off empty. We will be going through and adding all of the nodes, but once we have two nodes, we can link them together with this function. And so if there's no edges here from that node, if we haven't gotten to it yet, what we're going to do is self.edges.insert from node hash set new. What this allows us to do is essentially if we haven't added this node before, we are going to give it an empty association list, and then we are going to push to that. And we are going to run into some issues because we need to have a whole bunch of scaffolding here. We need eq partial eq hash at the very least on there. And because life is too short, we'll also add clone and copy because this should all be clonable and copyable. So link will go through our, we'll add the node to the graph effectively if we haven't seen it before, and insert the to node to it as well. So there's one more method that we're going to add, but we will postpone that for the moment. We first want to create this first follow. So let's do let first follows is first follows new of self. Of grammar. We actually need the nullables for this too, so let's do nullables is going to be we're going to calculate the nullables. We're going to calculate the first follows using those nullables. And once we have those, we can just use the convenience syntax to create the structure out of that. So let's look at what first follows is going to look like. For rule and rule, grammar. So for each rule, something special happens. For symbol in rule.rhs, we're going to iterate over the right-hand side of all of the rules. So here, bx, y, ab, here doesn't iterate at all because there's an epsilon, a. Oh, we need to know one other thing in our grammar, which is for the impl symbol, we need to know if this is a terminal or not. Is terminal. We will add a to-do there. So for each symbol on the right-hand side, if symbol is a terminal, the left-hand side will become a terminal with that symbol. Otherwise, if it's a non-terminal, we will kind of, in a sense, it kind of feels like a recursive situation here where either you're going to add the singleton or you're going to kind of pass it off in the case where first of A is first of B, we're going to link like that. And then as soon in our iteration here, as soon as we hit a symbol, if nullables contains symbol, if we hit a nullable symbol, we're actually going to break. Or no, as soon as we're going to go is other way around. As soon as we hit a non-nullable symbol, we should have taken care of everything that we need to. So this is handling the situation that C is going to iterate. It's going to iterate over A. It's going to see that A is nullable, and so then it's going to try B. But if you had another case where there was a non-terminal, C goes to, or what would it be? Like, I don't know, it doesn't make a difference. C goes to A, E, F. Because E, because E is, well, it's not. Let's just leave that as assumed for the moment. So yeah, we're going to go down the line and go until we find something that is not nullable. And then we sort of hit the base case for that. The next piece of logic is a bit tricky. So how do we want to approach that? So this is actually going to be like a section firsts as first are firsts. The second section is going to be follows are firsts too. What does that mean? That means we have this way of going about things. Symbol and rule.rhs.iter.copied.enumerate. For j and I plus 1 rule.rhs.len. Let follow equals rule.rhs sub j. And there's a lot of replication of this rule.rhs. We can go back and fix that up later and make it a little bit more efficient, but for the time being we're just going to leave it like that since it will work just as well. If the follow is terminal, do one thing, else do another thing. And this is going to be the same thing as building links. If it's terminal, then the follow of the symbol is going to be the terminal of the follow. Okay, so here we actually have two things. We've got two symbols in play. We've got symbol and we've got follow. And these are coming from pairs of symbols that are on the right-hand side. And we always know that follow has to actually follow. We start off at I plus 1, but then we're going to walk down the list. This is actually pretty confusing. I'm going to have to go into a little bit more detail and really flesh this out. Let me write the code correctly first. And then going through it a second time and explaining how this all works might be easier. So that looks correct. So when we are walking down the list, we're going to compare the symbol, and then the following one, we're going to grab the follow set for, we're gonna grab that follow as the terminal if it is a terminal. If it is a non-terminal, then we're going to grab the first of there. So the follow can sometimes, up here we see firsts are firsts, and follows can also be firsts. Here, what's important is that we are we are taking the first to the left-hand side here, and over here we are taking the first or the follow of whatever symbol we're currently pointing at. We will dive into that in more detail at another point, but the last case here, follows can also be follows. The final case that we have is for symbol in rule.rhs.into_iter.rev. So we're going to walk through the symbol list backwards. If the symbol is a non-terminal, we do one thing. If it is a, just keep the logic consistent, so we're always doing is terminal, is terminal, is terminal. Oh, no, in this case there is actually a reason we do that. It's because there is no else case. So in the case that we have a non-terminal, which we also need to define that. So if we have a non-terminal, we're going to add another link. And this link is going to be from the follow of that symbol to the follow of the right-hand side, of the left-hand side. But as soon as we hit a non-nullable symbol, we are going to break and leave that loop. So let's not dig too deeply into that. At this point, the graph is all built, so we're going to return first follows here. We don't need this grammar. Don't need that grammar node. So we are going to fail because we still have our is terminal, is not terminal, not implemented. So for the symbols, how do you know if something is a terminal or a not terminal? Is effectively, is there a rule that has it as its right-hand side? So we can do for rule in self.grammar.rules if rule dot we can do the non-terminal first, I think is the easier one. If rule dot left-hand side equals self, and we can pass it like so. Return true. And then whether it is non-terminal is it a terminal, non-terminal, terminal. We just negate the other one. So maybe that works. And analysis on line 26. This is where we're going to need the last little function down here in first follows. It's going to be terminals from node. So the terminals from is going to be a is it depth first search? Is it breadth first search? I forget. It's going to be just a walk across the entire graph, starting at the from node to get to the final set of terminals that are reachable from there. So we're going to do let mut visited is a hash set new. Let mut q is going to be a vector from node. Let mut terminals is going to be the hash set that we are going to return. And we're going to do while let some node. We're just going to pop off the queue. And we're going to say we visited that node so we don't get stuck in loops. If let node terminal symbol is that node. So only in the case that it's a terminal are we going to do terminals.push symbol. Otherwise, if self.edges.contains key node, otherwise we're going to look up all of the different edges that we see, and for each node that we find, each next node in self.edges node, if it's not visited, then we're going to push it onto the queue. And so then the set of first is going to be the self.firstFollows.terminals from, and we're going to do ff node first of that symbol. And then for this one, we're going to do from the symbol called follow. And now all of our tests pass. We'll leave it there.